On the 6th of June, 1816, snow fell on Albany, New York. Not a frost, not a cold rain. Snow, in the second week of June, in a city sitting at the same latitude as Rome. It fell on Dennisville, Maine, that same day. Within a week, ice was forming on standing water across New England. In Cape May, New Jersey, farmers recorded frost on 5 nights in a row and watched their crops die in the field. In Connecticut, a minister named Thomas Robbins wrote that the weather was so cold his asparagus refused to grow. In August, he woke to find frost on the ground. In Vermont and New Hampshire, families cut down whole fields of unripened corn just to feed their livestock as fodder. Thomas Jefferson, farming at Monticello that year, wrote that America had never known such a season in its history. And nobody, not Jefferson, not a single American scientist, not one European natural philosopher, had any idea why it was happening. The answer sat on the other side of the planet. 14 months earlier, and 11,000 miles away, a mountain on a small Indonesian island had detonated with more force than any eruption in recorded human history. The people freezing in New England had never heard its name. Most of them never would. It took science more than a century to connect those two facts. And in the process of connecting them, the study of Earth's climate became something it had never been before. It became a discipline that could be tested. This is the story of Mount Tambora, not just what it destroyed, but what it forced us to learn. If you find this channel worth your time, subscribing helps. It's free, and it tells the algorithm this kind of work is worth showing to people. Now let's get into it. Mount Tambora stands on the northern coast of Sumbawa, an island in what was then the Dutch East Indies, and is now Indonesia. It sits above a subduction zone, where the Indo-Australian plate grinds downward beneath the Eurasian plate, feeding magma into a chamber a few miles below the surface. Before 1815, Tambora was one of the tallest peaks in the entire Indonesian archipelago, with a summit estimated at roughly 14,000 feet. It had been quiet for centuries, and that quiet wasn't peace. Inside a sealed magma chamber, gas was slowly separating out of cooling rock, and pressure was building with nowhere to go. The eruption didn't begin on the 10th of April. It began 5 days earlier, with tremors and explosions loud enough to be mistaken for cannon fire hundreds of miles away. British authorities in Java, hearing distant booms, sent out troops because they believed a neighboring outpost was under attack. Then, on the evening of the 10th of April 1815, the mountain entered what volcanologists call its climactic phase. Here the numbers stopped being ordinary. Tambora ejected somewhere between roughly 30 and 50 cubic kilometers of magma. Counting the ash, pumice, and shattered rock that came with it, the total volume thrown out reaches somewhere around 150 cubic kilometers. That range is wide, and there's a reason for it. Different teams measure different things. Dense rock equivalent versus bulk tephra, and the deposits have been eroding for 2 centuries. What every estimate agrees on is the classification, Volcanic Explosivity Index 7, the highest category documented anywhere in the historical record since the eruption of Mount Samalas in 1257. The eruption column punched roughly 26 miles into the sky, well past the top of the troposphere and deep into the stratosphere. That detail is the entire story, and we'll come back to it. Pyroclastic flows, avalanches of superheated gas and rock moving at highway speeds, poured down every flank of the mountain and ran all the way into the sea. The village of Sanggar, roughly 15 miles from the summit, was effectively erased. When those flows hit the water, they displaced it, generating tsunamis that struck East Java and the Molucca Islands. Tsunami deaths alone have been estimated at around 4,600. Ash fell in a plume that reached Borneo and Sulawesi. Total darkness, in daytime, lasted 2 days across an area extending hundreds of miles from the volcano. The explosions were heard on Sumatra, roughly 1,600 miles away. And when it was over, the mountain was gone. Tambora had blown away its own upper third, dropping from roughly 14,000 feet to somewhere under 10,000 and leaving behind a caldera 4 to 5 miles across. A hole where a mountain used to be. The immediate toll on Sumbawa was somewhere around 10 to 11,000 people. killed by the flows, by suffocating ashfall, and by the waves. But the eruption didn't stop killing when it stopped erupting. Ash smothered farmland and poisoned water across Sumbawa and neighboring Lombok, and famine and disease followed for months. Estimates for the regional death toll vary a lot. A peer-reviewed review by the volcanologist Clive Oppenheimer puts it at over 71,000. Archaeological work in the 2000s, which uncovered a village preserved under 3 meters of ash, pushed some estimates toward 117,000. You'll see all of these numbers cited confidently in different places. The honest position is that the true figure is unknown, and that it's in the tens of thousands at minimum. That's what happened at the volcano. What happened next is what makes this a science story. Here's the thing that's genuinely difficult for a modern audience to absorb. The largest volcanic eruption in recorded history occurred, and the world essentially didn't find out. There was no telegraph. News from the Dutch East Indies traveled to Europe by sailing ship, taking months, and it competed with a rather large ongoing story. Napoleon had escaped Elba in February of 1815, and Waterloo was fought in June, 2 months after Tambora erupted. Reports did eventually reach European newspapers. Stamford Raffles, the British Lieutenant Governor of Java, collected accounts and published them. But those reports were filed as a distant colonial disaster, a tragedy on an island most readers couldn't locate. Nobody filed them as a climate story, because the concept of a climate story didn't yet exist. So when the sun turned pale the following year, when a persistent dry haze settled over Europe and North America, when the summer simply failed to arrive, people reached for the explanations they had. Some blamed sunspots, since astronomers had noted unusually large spots visible to the naked eye through the haze. Some blamed comets, or the total solar eclipse of May 1816. In New England, some preachers blamed sin. The volcanic explanation did appear in the European press, but not until 1817, after the worst was over, and even then as one speculation among several. There's no evidence that Jefferson, who tracked Virginia's weather with real rigor and complained that summer felt as cold as a mild winter, ever connected what he was recording to a mountain in the Dutch East Indies. Not because he wasn't clever enough, because the data required didn't exist, and neither did the framework to interpret it. That gap between an event and the ability to understand it is the real subject of this video. To understand what Tambora did to the atmosphere, you have to understand the difference between ash and sulfur. Ash is heavy. Volcanic ash falls out of the sky within days to weeks. It's devastating locally and irrelevant globally. The popular image of an ash cloud blocking the sun for a year is essentially wrong. Sulfur dioxide is different. Tambora injected an estimated 60 megatons of sulfur into the stratosphere, roughly 6 times what Mount Pinatubo released in 1991. Up there, above the weather, there's no rain to wash it out. The sulfur dioxide reacts with water vapor to form tiny droplets of sulfuric acid, and those droplets are almost perfectly sized to scatter incoming sunlight back into space. They spread. Within months, the aerosol veil had circled the globe and reached both hemispheres. And it stayed for years, because nothing in the stratosphere removes it quickly. The effect on global average temperature was, in absolute terms, small. A few tenths of a degree Celsius across the planet as a whole. Hold on to that, because it's the most important number in this story. A few tenths of a degree. Regionally and seasonally, that small global shift concentrated into something catastrophic. European and North American summer temperatures in 1816 ran a full 1 to 3 degrees Celsius below normal, and crops don't care about global averages. Crops care about whether there's a frost in July. There was. In New England, 1816 entered folk memory under 3 names: the poverty year, the year without a summer, and the one that stuck, 1800 and froze to death. Hard frost in every month of the year. Temperatures in July and August dropping into the 40s Fahrenheit as far south as Connecticut. On the 5th of June in Ipswich, Massachusetts, the temperature hit 92 degrees, and by the next morning it had fallen to 43. The corn failed. When it grew at all, it never ripened. What little grain was raised got eaten, which meant there was no seed for the following spring, so the failure compounded itself. Oat prices in some areas rose from 12 cents a bushel to 92. Not enough hay was cut to feed the cattle, so families slaughtered their livestock, which solved one winter and ruined the next. In New Hampshire, a farmer named Reuben Whitten raised 40 bushels of wheat on a south-facing slope and shared it with his neighbors. When he died in 1847, those neighbors paid for his gravestone. The inscription, spelling and all, records that his wheat kept his family and his neighbors from starvation. That's what the year meant at ground level. Europe had it worse, because Europe was already broken. The Napoleonic Wars had just ended after 2 decades of disruption. Granaries had been raided. Harvests had been poor since 1812. Then 1816 brought a cold, sunless, relentlessly wet summer. Grain prices in Switzerland tripled. Several European governments formally declared famine. There was rioting, arson and looting across Britain and France, and food riots in Germany. Typhus followed, the way it always follows malnutrition and displacement. This was, by most accounts, the last great subsistence crisis of the Western world, and it wasn't confined to the Atlantic. In China, the Yunnan region suffered catastrophic rice failures. In India, the summer monsoon was disrupted, and that matters for reasons we'll get to shortly. Enormous disruptions leave strange fingerprints. Some of Tambora's are well documented. Some have been repeated so often they've hardened into fact without ever earning it. Start with the one that's solid. In June of 1816, a group of English writers were staying at the Villa Diodati on the shore of Lake Geneva. The weather was so persistently cold, wet and dark that they couldn't go outside. Confined indoors, they entertained themselves reading ghost stories aloud, and their host proposed that each of them write one. One of the party was 18 years old. Her name was Mary Godwin, shortly to become Mary Shelley. What she wrote that summer became Frankenstein. Another guest, John Polidori, wrote The Vampire, which established the template for essentially every literary vampire that followed. 2 of the founding texts of modern horror were written in the same room, in the same week, because a volcano in Indonesia had canceled the summer. This isn't folklore. It's cited in the scientific literature on volcanic climate impacts, and the meteorological records for Geneva that summer have been reconstructed in detail by climate historians. Then there's migration, and this one is well supported. Thousands of New England farm families, having watched 2 growing seasons fail, gave up. They moved west, to western New York, Ohio, Indiana, and Illinois, where the cold had been less severe and the soil was deeper. The year without a summer didn't start the westward migration, but the historical consensus is that it substantially accelerated it. The demographic map of the American Midwest was redrawn in part by a volcano. Now the 2 that need careful handling. The first is cholera. In 1817, a cholera pandemic emerged from the Ganges Delta and eventually spread across Asia and as far as Russia, the first of the global cholera pandemics. The hypothesis is that Tambora's disruption of the Indian monsoon altered the ecology of the delta, creating conditions for a more virulent strain to spread. This is a serious published hypothesis, argued at length by the historian Gillen d'Arcy Wood. It is not settled science. Cholera's emergence involved trade routes, troop movements, and population pressure alongside any climatic trigger, treated as plausible and contested, not proven. The second is the bicycle. You've almost certainly heard this one. The year without a summer caused a hay shortage across Europe. Horses starved, or were slaughtered for meat. With ground transport suddenly unreliable, a German civil servant named Karl von Drais set out to build a machine that could replace the horse. In 1817, he unveiled the Laufmaschine, the running machine, a 2-wheeled, steerable, human-powered vehicle. On the 12th of June 1817, he rode it from Mannheim toward Schwetzingen and back, covering roughly 8 to 9 miles in under an hour, at a quarter of the usual travel time. That machine is the direct ancestor of the bicycle. Add pedals decades later, and you have the modern bike. All of that is true and well documented. The part that isn't secure is the causal claim, that the volcano is why he built it. That claim traces primarily to Dryas's biographer, Hans Erhard Lessing, who proposed the horse shortage motivation. It's been picked up by the Smithsonian, by engineering societies, by cycling organizations, and by essentially every popular account since. It makes a wonderful story. Ecological catastrophe on one side of the world, invention on the other. But Dryas had begun building human-powered vehicles in 1813, 2 years before Tambora erupted. His early attempts were four-wheeled carriages. The two-wheeled breakthrough came out of an existing line of work, not out of nowhere. And cycle historians have gone on record saying the Tambora inspiration is now generally regarded within their field as unsupported by the evidence. Even Lessing's own framing situates the horse shortage within a broader crisis. The Napoleonic Wars, the raided granaries, the poor harvests running back to 1812. So here's the accurate version. Dryas invented the ancestor of the bicycle in the immediate aftermath of the worst subsistence crisis in modern European history, in a Europe where horses were expensive and food was scarce. That context is real. Whether the volcano caused the invention is a claim historians of the bicycle have largely stopped defending. We're flagging it because you'll see it stated as fact almost everywhere, and because a story this good deserves to be told accurately, rather than conveniently. Now we get to the part that actually justifies the title. Tambora didn't change science in 1816. It changed science slowly, over roughly 170 years, by becoming the most useful natural experiment in the history of climate research. The idea that volcanoes could cool the climate wasn't entirely new. In 1784, Benjamin Franklin, then in Paris, wrote about the persistent dry fog hanging over Europe and speculated it might be connected to a volcanic eruption in Iceland. He was thinking about Laki, and he was broadly right. But it was a guess offered without a mechanism, and it went nowhere. Through the 19th century, the pieces accumulated slowly. When Krakatau erupted in 1883, the Royal Society commissioned an enormous investigation, including watercolor paintings of the extraordinary sunsets seen over London, and charts of the pressure waves circling the globe 4 times as recorded by barographs. That was the first time a single eruption had been studied globally and systematically. In the early 20th century, the American physicist William Humphreys worked out the physics properly. It wasn't the ash but the fine sulfate aerosols high in the stratosphere that mattered, because they scattered incoming solar radiation while letting the Earth's own heat escape. By the 1970s, the climatologist Hubert Lamb had compiled what he called the Dust Veil Index, ranking historical eruptions by atmospheric impact using historical records, temperature series, and observations of optical effects. Tambora sat at the top of it. For the first time, the eruption and the year without a summer were formally quantitatively linked. And then came the ice. This is the part that changed everything. When snow falls on Greenland and Antarctica and compacts into ice, it preserves, layer by layer, a physical record of what was in the atmosphere at the time. Drill a core, count the annual layers like tree rings, and you can measure sulfate. Tambora is unmistakable in the ice. There's a sulfate spike in both Greenland and Antarctic cores, and it's enormous. Research on Greenland cores from 11 separate locations documented the Tambora signal alongside Laki. And crucially, the cores let researchers date the deposition subannually. The sulfate arrived and settled over roughly 16 to 25 months, with the midpoint falling in the second half of 1816. That's a physical chain of custody linking a specific mountain to a specific summer. Suddenly, the story wasn't a historical inference. It was a measurement. And then the measurement broke the story. When researchers looked closely at the ice core record around Tambora, they found something they weren't expecting. 6 years earlier, in 1809, there was a second sulfate spike. It appeared in both Greenland and Antarctic cores at nearly the same time, which is the signature of a large tropical eruption injecting sulfur into both hemispheres. There's no volcano attached to it, no eyewitness account, no named mountain, nothing in the historical record. And yet by the sulfur numbers, this unknown eruption ranks as the third largest since 1500, with a stratospheric sulfur injection estimated at roughly twice that of Pinatubo, and perhaps 30% less than Tambora itself. This matters enormously, and here's why. The 1810s are, on the available evidence, probably the coldest decade in the last 500 years. Tree ring analysis from high-elevation Swiss stone pine puts them as the coolest summer decade in Central Europe in 3 centuries. For a long time, that entire cold decade was attributed to Tambora. They predicted that intense aerosol cooling would begin late in 1991 and reach its maximum late in 1992, and that it would be large enough to temporarily overwhelm both the ongoing greenhouse warming trend and a developing El Niño. And then everyone waited. The observed global cooling came in at roughly half a degree Celsius, peaking in 1992. The model had slightly overestimated the magnitude. The timing, the shape, and the scale were essentially right. This was one of the first genuine out-of-sample tests of a global climate model. A prediction published in advance, about a system nobody controlled, verified against what actually happened. It didn't prove climate models were right about everything. It did demonstrate that the physics of how the atmosphere responds to a radiative forcing had been captured correctly. And the reason anyone knew to run that test, the reason volcanic forcing was a recognized category worth modeling at all, is a chain that runs directly back through the ice cores, through Lamb's index, through Humphreys' physics, through Krakatau, back to a summer in 1816, when snow fell in June, and nobody could explain it. In 1815, world population was roughly 1 billion. Today it's over 8 billion. Modern agriculture is vastly more productive per acre, but it's also far more centralized, far more dependent on a handful of major breadbasket regions, and far more reliant on global trade to move calories from surplus to deficit. That cuts both ways, and it's worth being honest about it. Global trade is a real buffer. A bad harvest in one region can be covered by a good one elsewhere, in a way that was impossible in 1816. But it's a buffer that assumes the shortfalls aren't simultaneous, and a stratospheric aerosol veil doesn't respect breadbasket boundaries. It cools the entire northern hemisphere growing season at once. Researchers have taken this seriously enough to use 1816 explicitly as a modeling scenario for testing the fragility of the global wheat and rice trade. That's the part worth sitting with. The year without a summer wasn't just a disaster. It was a question that took science almost 2 centuries to answer properly, and answering it built the tools we now use to understand what the climate is doing right now. The mountain is still there. It has a lake in its caldera, and a monitoring station on its flank, and it's one of dozens like it. We're better prepared than we were in 1816. We'd also have a great deal more to lose. Thanks for watching. If this was worth your time, go ahead and subscribe. It genuinely helps this channel reach people. See you in the next one.